Good day, everyone. Today we shall be considering physical quantity 1. Under this, we shall be considering the following: 1. Introduction to physical quantities, classification of physical quantities, obtain the units of derived quantities, and introduction to dimension. Okay, so welcome to our physics class. I want to say that today we are looking at measurement, and what we'll consider briefly is units and dimension. Firstly, I want to say that physics is characterized with measurement of several quantities. Yes, when we talk about physics, we talk about several quantities: mass, length, time, acceleration, force. Most of the things we talk about in physics are quantities, and we try to measure out these quantities. Well, these quantities can be classified into fundamental quantities and derived quantities. Now, what are the fundamental quantities now? The fundamental quantities are quantities which are independent of all other quantities. Means that they are on their own. They are not gotten from other quantities. They are independent, just on their own. Yes, that's the fundamental quantities. And so you don't. It simply actually means that you don't get them from anywhere. Yeah, they don't get them from anywhere. They just self-exist by themselves. That's what the fundamental quantity is all about. So, all other quantities apart from the fundamental quantities are gotten from the fundamental quantities. So, well, as you proceed, you understand clearer. And so, but the units of the fundamental quantities are called fundamental units. I want you to take note of that. And what that simply means is that what you call the singular value of something, like for instance, now if I'm talking about force, a unit of force, just one value of force, what do we call it? That what unit is all about. So the units of fundamental quantities actually are called fundamental units. And what are examples of these fundamental quantities now? Mass, length, time, temperature, luminous intensity, electric current, amount of a substance. There could be more actually. These are the basic ones we know, but there could be more fundamental quantities. So, but you don't need all that. So these are the 7 basic fundamental quantities. So these quantities did not get them from anywhere. They just self-exist by themselves. But all other quantities are gotten by combining one or two of these quantities. So the table below will show us the fundamental quantity and its unit. And so this is what we have: the fundamental quantities and their fundamental units. Mass is kilogram, kg. Anyway, you see kg, you should be talking about that what was measured was actually mass. When you say length, it's meter. And so anytime you see meter, have it in mind that what was measured is length. Actually, when we say length, length connotes both or stands for both distance, displacement, and breadth, height, all those things are all anything measured in meter is just categorized under length. So when you see length, have it in mind that I'm not just talking about length alone. Distance is included. Displacement is included. Height, base, whatever depth, anything measured in meter, you are categorized into length. So that's that about that. So I can ask you, what's the unit of distance? You say, I didn't see distance as fundamental quantity. No, it's inside the length. So that's that about that. Now we have time. Time is second. Temperature, Kelvin. Electric current, ampere. Amount of a substance, mole. And luminous intensity is candela. So that's that about that. Let's look at the derived quantities now. So the derived quantities now, these are quantities which are dependent on the fundamental quantities. They are called derived quantities because you get them from or you derive them from the fundamental quantities. So it's either you combine one or two or more fundamental quantities, and that way you get the derived quantities. And the units of derived quantities are called derived units. I want to still say that you can be asked, quantities are classified into what? Into what? So fundamental quantities and derived quantities. Even units can be classified into fundamental units and derived units. What are fundamental units? They are the units which are independent of all other units. They are the unit that self-exist by themselves. Example of fundamental units are what we've talked about: kilogram, second, ampere, candela, all of those unit of the fundamental quantities. So take note of that. And we have derived unit. These are the units of the derived quantity. They are units which are dependent on the fundamental quantity. So have that in mind. I just want to make the note bulky. That's why I didn't talk about units separately. So the table below actually will give us derived quantities and their units. Let's take note now. Okay, so we shall be looking at the following derived quantities: area, volume, density, velocity, acceleration, all, so many of them, and we'll look at how we get their unit. This is very, very important because so quite number of persons, you see them calculating something, maybe they are solving for velocity, and by the time they finish solving for velocity, maybe they get 20, they just leave the answer as 20. They ought to know that the unit of velocity is meter per second. So by the time you write 20, you should be writing meter per second beside it. So all this is very, very important. In fact, whenever you ask me to teach physics, I'm going to do physics, I try to first of all take this, because I cannot calculate. I cannot see you calculate force without putting Newton. How do you want somebody to know that force you've calculated? The unit should also be telling what you calculated, apart from writing the fact that F is equal to. No, we should also know from the unit of what you've done. And so that's that about that actually. But let's look at these quantities and then tell their unit. For the first one, actually, area, you see it contains two fundamental quantities, length and breadth. Like I told you, length and breadth are all the same thing, all categorized under length actually. So length, what's the unit of length? The unit of length is meter. And the unit of breadth is also meter. So at the end of the day, we have what we call meter square as the unit, meter square. So we also have volume. Unit of volume is m, m, m. Unit of volume, length times breadth times height, and all of these things are calculated under the same thing. So write as meter cube. Density, what's the unit of density? It is kilogram. Mass, mass is kilogram, so kg, and volume is meter cube, m cube. So at the end of the day, we have kilogram all over meter cube, or by indices, we can write as kilogram. The meter cube comes up to become -3. This is one of the law of indices. The meter cube comes up to become m raised to the power -3. And so we have velocities now. Velocity displacement over time. Displacement is also categorized under length. So distance, displacement, breadth, height, whatever, all categorized under length. So displacement is meter, while velocity is seconds, time is seconds, sorry. So I'll write that as meter per seconds, or using indices, I can also write that as mx raised to power -1. So it means that any day you see something having meter square, maybe I say 20 meters square, that must be area that is being measured. Any day you see me writing volume, writing 30 meter cube, that must be volume that is measured. It can be centimeter cube, it can be meter cube, it can be dm cube, but that is volume. So this is very, very important actually. Let's look at acceleration now. For acceleration, is velocity over time. That's the formula. So you must know the formula before you can tell the unit actually. So the formula for velocity is meter per seconds, as we've done before, meter per seconds, and that of time is seconds. So at the end of this, like having something that looks in this manner: m over x divided by another x. This x will jump down to become m over x times x. What has happened? That this x here jumps down. That's what happened. And then it can be written as meter all over second square, or by indices you say meter per second square. You can write like this. So the next one we have is force. Obviously, force is mass times acceleration, and mass is kg, and acceleration is meter per second square. Meter per second square. That's just the one we just finished doing now. So this will be kilogram meter per second square. And I want to say this can also be written as kg. Kg, yes, kg indices, kg meter per second square. But we have another unit for force, which can also be Newton. So when they see kg meter per second square, that is force. When they see Newton, that is force. N, you can see you write 20 N, 30 N, that is 30 Newton. That's force actually. Then we have pressure. pressure is actually force over area. And you know, force is measured in Newton, area is measured in meter square. So at the end of the day, it's giving us Newton all over meter square, or using indices Newton per meter square. So we should be able to do this using the formulas we have. You can try many. Okay, and so we have our pressure lastly done, which is the Newton per meter square. Now looking at work. Work is force times distance. Remember that force is kilogram meter per second square. We did that previously. And then distance is meter. If you multiply all this, you will get kilogram. Then meter multiplying meter will give meter square. And then per second square. That's depending if you want to use that. Again, we can just assume that, or we know that force is Newton and work is meter. That will also give us Newton meter. But again, we have an SI unit for work, which is joules. So you can take note of that. Joules, J. And so anytime we look at work, we use joules for work. We have energy too. Energy, mass times gravity times, I'm using potential energy, we say that's mgh. There's also kinetic energy, but whichever one we use, you get the same unit. And now remember that mass is kg, and also gravity is meter per second square, and then height is meter. And when you multiply all of this, you get kilogram meter square per second square, which is the same as joules as well. So the unit of energy is joules. Please take note of that, joules with a J. So anytime you see 30 joules, that should be talking about either work or energy. We also have force. Force is given in Newton, and then distance in meter. So moment is given as Newton meter. Moment is not given as joules, even though it has the same derived unit for work. It's not given as joules. Anytime you calculate for moment, you write Newton meter. And take note that moment is force times perpendicular distance. And remember, if you like be perpendicular distance, if you like be horizontal distance, all distance are measured in meters. So that's why it is Newton meter. And so there are many of these things, and I'm going to show you that you can try to memorize that and get that by yourself. I'm going to write so many of them, and then you can write their unit too. There's no need to start taking much of time doing that, but let's look at them below now. Well, we can't exhaust the list, but you see, we have power now. Power is work over time, which is work in joules, and time in seconds, joules per seconds. Or it has an SI unit of written as watts. Then we have momentum. Momentum is mass times velocity, mass in kilogram, velocity in meter per seconds, and that gives us kilogram meter per seconds. We as well have surface tension, Newton as force, and length as meter, because surface tension is force per length, Newton per meter. And then we have heat energy, heat capacity, sorry, which is heat energy over temperature. But heat energy is just energy, which is joules, and temperature is Kelvin, joules per Kelvin. And so the list is so much. We have some other ones that are not written here, and we'll quiz you about just what's beyond here. So I want you to go through your physics textbook as well, and then check all of those other quantities which we have their units written out. So try to know their units, because we'll work on every one of them as we participate in today's learning activity. Beyond that, now we want to move into dimension. So right now we're looking at dimension now. What is dimension? The dimension of a physical quantity is the relationship between the physical quantity and the basic unit. Well, as we progress, you understand what this definition is talking about. But basically, what dimension does is that it takes a quantity and tells you how the physical quantities are playing, how the fundamental quantities or basic quantities are playing in that physical quantity. For example, now it takes volume and tell you how length is playing in that quantity.
It takes acceleration and tells you how mass or length or time and the rest are playing in it. That what is the definition is really saying. But as we progress, like I said, we begin to understand why we defined dimension as that. Okay, now the table below actually gives us some of the dimensions we have. And here are they now. Some of the fundamental quantities and their dimension. We have mass, the dimension is m. We have length, the dimension is l. We have time, dimension is t. Electric current, dimension is a. Temperature is theta. And amount of substance is n. Please don't confuse this dimension with unit. Unit of mass is kg, not m. Unit of length is meter, not L. So dimension and units are two different things. So let's take some derived quantities now and get their dimensions. So now let's look at some derived quantities and their dimension. Now, as we look at the first one, area, well, the dimension, area is length times breadth. The dimension for length is L. And when we say length, we both mean length, breadth, height, radius, diameter. Anything measured in meter is length. So dimension is L. And then breadth is L as well. So the dimension becomes L square, meaning L times L, L square. Now for volume, length, breadth times height, that's L multiplied by L multiplied by another L. So for volume, length times breadth times height, that's length, that's L cube. For density, it's mass over volume. Now, you know mass now, the dimension is m, please not unit. Unit is kg, dimension is L. Volume is L cube. So eventually we have m L minus 3. Again, velocity. Velocity is displacement over time. Displacement is measured in meter. So dimension should be L. And time is t, L over t. So we have L t minus 1. Okay, so let's progress still. We also have acceleration. Acceleration is velocity over time, but we've just previously done velocity as L t minus 1. That's the dimension. And then time is t. So eventually, this t moves up to give us L. The t at the denominator moves up to give us LT minus 2. Because there's a minus 1 before. This one moves up to give us minus 1 again. That's minus 1 with the previous minus 1 t. That will be minus 2. Force is mass times acceleration, and mass is m, while acceleration is lt minus 2. So everything gives us m l t minus 2. That's for force. Then we have pressure now. Pressure is force over area. And force is giving us m l t minus 2 with area L square. We just did area as our first dimension we look for. And so that will give us, this L square moves upward, that it become L minus 2, and there's an L before. So that will give us M L minus 1 T minus 2. Hope you understand. I mean, this L here cancels one of the L here. So we just have one L down. When this one L goes up, become L minus 1. That's why we have L minus 1. Again, we have work. So what is work? Work is force times distance now. Force is M L T minus 2. Distance is L. Eventually, the dimension become M. L times L will give us L square. And then T minus 2. We have energy too. Energy is mass, gravity times height. That's potential energy. So again, mass is m, gravity is acceleration to gravity. Acceleration is lt minus 2, and then height is l. So we have m l square t minus 2. Now we have moment. Moment is force times perpendicular distance. What is force now? Force is m L t minus 2, and then distance is L. So again, we have m L square t minus 2. Okay, and then
On and on, we have momentum. Momentum is mass m and velocity lt minus 1. That is mass times velocity. That is m lt minus 1 now. That's the dimension. We also have stress, which is force over area. Force m lt minus 2 over area l square. So eventually, one of these L cancels one of the one down, and then we have M L minus 1 T minus 2. Okay, so power now, power is work over time, and then we know that work is M L square T minus 2, then over T, and that will give us M L square T minus 3. And the last one we have here for our study here is force over length. And we know force now. Force is lt minus 2 over length L. L cancels out L. We have mt minus 2. So there are many more actually. We have viscosity, we have uh, luminous intensity, we have so many of them, so many of them. Well, luminosity is not a derived quantity, it's a fundamental quantity, sorry. But we have so many of them. We have specific capacity, we have heat capacity, and so you need to know every one of them actually for your exam and for this small quiz we even have here. You need to actually know them. We can't exhaust them here, but these are the ones we would give to you. So the next thing we want to look at actually now is the uses of dimension. That is the last thing we'll talk about in dimension in your textbook. I want you to also know this study is the first study you will do on campus. You know it now. They will give once you finish, they will give you assignments. Once you know it now, you can flex your muscle even when you get to campus. So that's that about that.